Good morning to all of you. Okay, okay. So today we are going to start a new understanding a new concept in spectroscopy, that is magnetic resonance spectroscopies. So in this category we have two techniques that that is based on magnetic resonance, the phenomena that is NMR and EPR. EPR is also sometimes called electron spin resonance or electron paramagnetic resonance. So the underlying techniques is underlying concept is basically the same. So what is that? Yeah, let's try to learn about that thing. Okay, so resonance, what it means? Suppose if you have a pendulum like this, okay, first figure that you are seeing. So you give a jerk and it starts oscillating. Now you, besides that, if you can put a small pendulum with a smaller length L, like this, and then which is connected to the same thread, same rubber string. It is a rubber string, the same rubber string to which the first thread was uh, hanging. You attach another one on a little away on the same string, थोड़ा सा दूरी पे उसको लगाया आपने. Now if you give a jerk and uh, this pendulum starts rotating, starts oscillating, you will also find that this one, the other pendulum over here, other string which was here, you haven't done anything. It was just lying it by itself uh, at rest, but suddenly you find that this one is also starts oscillating. So this phenomena is and then if you change the length, gradually keep changing the length of this thing. आप सिर्फ एक को ही move कर रहे हो. You only have to move this one and you will find that this one is also starts moving. Some energy starts, this will stop and this will start moving after some time. So there is some energy transfer that happens that we know as resonance. So how it happens, that's interesting, and it is a very basic thing that you in your physics experiments you have been doing in class 11th and 12th, I think. Okay, so resonance is something tuning fork experiment or something like that. Remember, you must have done in your schools. And just so pendulum is in the figure first, and you have another pendulum placed side along the same side, which is connected to the same base, this is rubber string. So giving a jerk to the pendulum A, first one, you will find that slowly it slows down and the other one which is attached over here, it starts moving. So there is some sort of energy transfer that happens, and if I vary this length of L, this small L, if it is, suppose it is varied, so starting from this small length and you go on increasing and such that it becomes equal to this length, if it is also equal to L. So this is the thing that I am saying, that if the length is varied and it is made same as the other pendulum which we are giving a jerk and it starts moving, then it is found that the amplitude, if you follow the amplitude of the that it moves, is maximum. So this is the length L. Variation in the length of this second pendulum is plotted on the x-axis, and on the y how much it moves, the amplitude. This is the actually the amplitude we are talking about. So when the length is small or length is higher than the capital L, then it is the amplitude of the pendulum is less. That means the energy transfer is to a lesser extent. But when the length of this thing is equal, then you have maximum amplitude is seen. The other pendulum vibrates with maximum amplitude, and then we say that the energy transfer is most efficient at this particular thing. So this situation, when you have exactly matched the so in a string you can define the frequencies, and L is something that comes into it. So the pendulum of length L, so this is called forced oscillation, or what we are seeing, that other pendulum is just without doing anything it starts moving, and it is, so this is illustrated through this. You can see one becomes slower and other one gains the energy. So initially start with the red one, and then you find red one slows down, green one starts moving. So if something like this happens. So this is an example of uh, so if the lengths are equal, the energy transfer is most efficient, the amplitude of vibration is more. If you take the pendulum, the side pendulum is of anything other than this, if the length is not matched, then energy transfer is less efficient. So this is the idea that from classical mechanics, that is still you take it, this the essence of this is taken in even in the quantum mechanics, or in, okay, so this is what makes it so variable length of the pendulum, and R is the amplitude. This is what I was saying. So the forced oscillations are communicated through the medium, the rubber, in this case classical sense. Now when we are talking about electromagnetic waves, the same thing can happen through empty spaces. We don't need a medium. Okay, so such things can happen, and we have found so uh, yeah, this point that yeah, I have told you the maximum amplitude, the second pendulum has oscillates with maximum amplitude when its length is made equal. So you can find the energy and other things. So energy transferred, if you calculate, is proportional to the displacement, so r square and all that. So the idea is that uh, the phenomenon of maximum absorption of energy that is happening when L is equal to L, maximum energy is absorbed when the small l of this L is equal to L. That in that scenario we are having the maximum absorption, and this maximum absorption of energy, maximum transfer of energy that you are seeing. So this is called resonance. This is called resonance phenomena, and the maximum absorption of energy by force system when its natural frequency is forced on it. So the the frequency of the two natural frequencies of oscillation is matched, and you have maximum transfer of energy happening. So this is the resonance. So in other words, we say that frequency, the length is also related to the frequency of the pendulum. You go back to the basic equation, you will find that frequency is related to, so we can also say that energy transfer is most efficient when the frequencies are identical. Okay, and so this condition of achieving this thing is called, when the two frequencies are matched and energy transfer occurs, is called resonance. Okay, in this case, in case of a simple pendulum, you are matching the length and you are achieving that thing, and the energy is transferred through the medium, here the rubber string. But electromagnetic field, if it is there, if you are talking about electromagnetic field, then it can travel through space without any medium, and such phenomena observed. So you see all the things that tuning that you do in radios, that is an example of resonance. Again, the transmitter is uh, yeah. So this is also the basis. Resonance is also the basis of your spectroscopic transition. Remember the microwave absorption, the microwave spectroscopy, infrared spectroscopy that we have discussed. All those are examples of this thing. You are matching the frequency uh, of the rotational frequency or the vibrational frequency, and then of you are getting, so as required by the energy levels, you are trying to match those oscillations, and then if the photon also has the same frequency, then the energy is absorbed. So resonance occurs there also. बस अंतर यही है कि उसके नाम के आगे रेजोनेंस जुड़ा हुआ नहीं है, लेकिन वो भी एक रेजोनेंस फिनोमेना ही है। ठीक है, ध्यान से पढ़िएगा, बैनवेल में लिखा है that. Okay, so now we are talking about conventionally. In this particular case, in where magnetic energy transfer is happening, they have resonance attached to their names. But the resonance phenomena, what we realize now, is a basic thing that has been happening in all the spectroscopic transitions, spectroscopic techniques that we have. We can talk about microwave spectroscopy, IR spectroscopy, or electronic spectroscopy. You were having this kind of thing already happening. Okay, you were trying, so this matching of the frequencies that we were talking about in two pendulums, the same thing, similar thing we were trying to do by matching the oscillation of electromagnetic field to a set of energy levels. So two energy levels, their so frequency and the frequency of the electromagnetic waves that we had. So if they are matched, then the absorption happens, a strong absorption occurs, and this is the resonance that we are talking about. So similar thing also happen when we talk about nuclear or electronic spin states. So now those were transitions that was related to electric dipoles. We were saying that there must be creation of electric dipole moment whenever the transition occurs. So that was uh, s- interaction of the waves. So it was the electric field component of the electromagnetic wave, electric field component of the light that was interacting and resulting in infrared spectroscopy, that is a vibrational transition, microwave spectroscopy, that was rotational transition, or electronic spectroscopy was happening. Okay, but here the one that we are going to talk about, it is the magnetic part of the light, the magnetic field, oscillating magnetic field, which will come into picture, and it is the oscillation of that magnetic field vector that we are talking about here when we discuss EPR, NMR, such techniques. It is the other component of electromagnetic radiation which has not yet come into discussion. So that part will be affecting. So the magnetic component in this electrons, nucleus, whatever if you have, there will be some. So that oscillation of magnetic field vector will interact with a magnetic dipole, and you will have energy transfer occurring. ये एक बड़ा डिफरेंस है, नोट द डिफरेंस, कॉपीज में लिख लो, ये कहीं नहीं बताया जाएगा. और अक्सर ये कन्फ्यूजन बाद में रह जाती है कि ओके, सो दिस इज यू आर गोइंग टू हैव, पिछली बार हम सारा कहते थे इलेक्ट्रिक फील्ड हर बार बोलते थे यही, ऑसिलेटिंग इलेक्ट्रिक फील्ड इंटरैक्ट्स विथ ऑसिलेटिंग डाइपोल, विच डाइपोल, इलेक्ट्रिक डाइपोल, पॉजिटिव नेगेटिव हम देखते थे। अब यहाँ पे हम लोग क्या करने जा रहे हैं, वी आर गोइंग टू टॉक अबाउट द magnetic field vector of the light waves, and the magnetic dipole that is developed. डाइपोल दो तरह के हो सकते हैं, इलेक्ट्रिक डाइपोल, मैग्नेटिक डाइपोल। सो यहाँ पे मैग्नेटिक डाइपोल होगा और वो मैग्नेटिक फील्ड वेक्टर जो लाइट में है उससे इंटरेक्ट करेगा। ये फंडामेंटल चीज है, ध्यान देना। सो यू मस्ट, हेलो, okay, so this is an important part of न्यूक्लियस। ओके, कंटिन्यूएशन में चल रहा है ना ये, अच्छा है, इसमें रिकॉर्डिंग को पॉज कर सकते हैं। सो या हाँ, सो ये कहने का मतलब ये है कि इट इज जस्ट दैट इट कैरीज द टर्म रेजोनेंस, इलेक्ट्रॉन स्पिन या न्यूक्लियर स्पिन से जुड़ा हुआ जो ट्रांजिशन है, देयर इज मैग्नेटिक, एंड जस्ट बिकॉज हिस्टोरिकली पहले कभी किसी ने इसके साथ रेजोनेंस टर्म यूज किया, इसलिए आज भी हम कैरी कर रहे हैं उसको। इलेक्ट्रॉन स्पिन रेजोनेंस, इलेक्ट्रॉन न्यूक्लियर मैग्नेटिक रेजोनेंस word is used, but what you should realize that resonance phenomena is not just attached to this concept, it was also attached to previous concepts which we have already learned. Okay, so it is uh, so it is attached here in this the names. Okay, bringing you have energy levels, and then the difference of energy levels brought into resonance with the fixed electromagnetic field. That is the formulation that has been used earlier and even now. The difference here being that now we are having a magnetic field vector interacting with the magnet spin and orbital momentum, wherever it is, magnetic moment of the electron or protons or neutrons, whatever. Okay, so it is the, for if we are discussing about electrons, you have two components, the spin angular momentum, orbital angular momentum. Okay, so momenta यहाँ पे लिखा है, momenta is plural of momentum, so momenta, and it is the spin angular momentum, orbital angular momentum, which gives rise to magnetic moment. Or you can say that this magnetic moment is proportional to the spin angular moment and the orbital angular moment. So that is, or you can say that this electron behaves as a tiny magnet, just like a small magnet it behaves. The protons or neutrons all behave as tiny magnets because they have spins. uh, Electron in addition has orbital angular momentum, and we should learn how this field is set up, how the magnetic moment is generated, and then we'll learn about what happens to the field is applied. So strength of the external field can change the energies of electron and nucleus. So uh, so magnetic field, if you classical, in classically, the energy of the system when in an applied magnetic field is given by B is the magnetic field, and mu is the magnetic moment. This is the magnetic symbol of magnetic moment, and B is the magnetic field. Magnetic field. So magnetic moment, the scalar product, it is the not a vector product, it is a dot product, you can see. So these two are vectors. You can see that magnetic moment is a vector, this is also a vector, and it is the dot product which is a scalar quantity that gives you energy. So mu into B with a negative. So quantum mechanically, if you want to establish that, we have to define a operator, Hamiltonian operator. So using that classical formulation, we can also define our energy operator for to find this magnet stored in the in form of magnetic field. So mu operator, this so mu bar is the mu cap that you are seeing is the operator that we can define, which is, so if that is the thing, then you can have so if so what you see here, this is an electron, and it has, so the vertical arrow that you are seeing like over here, this is the this is the orbital angular momentum L, orbital angular momentum, and this small s that you are seeing is the spin angular momentum. Okay, so what you are seeing here, so this is an isolated case. When the magnetic, if you apply the magnetic field, then you will find that it generates certain magnetic moment, and that magnetic moment generated is proportional to the small l orbital angular momentum. So the magnetic moment generated in an applied magnetic field, this will happen. This is the magnetic moment, and this is proportional to angular momentum. Angular momentum of what? This is the orbital one, due to the orbital motion. And similarly, you will also find that mu is also proportional to the spin angular momentum s. Okay, so both you can have a proportionality that you are seeing, and because the charge is, it is opposite charge having a, so the magnetic field moment that will be generated will be opposite to the direction. So this green arrows that you are seeing is this, if I may do this further, so when you remove the proportionality constant, you can think of mu will be equal to something, a proportionality called, so here this proportionality constant is called gyromagnetic ratio. Magnetic ratio. Okay, so this is a proportionality constant that comes in. So it is the orbital angular momentum is when it interacts with the magnetic field gives rise to magnetic moment 1. Similarly, spin angular momentum interacts with the of the electron, interact, it is the origin of another magnetic moment. So this is again, you have another proportionality constant, and in addition, magnetic moment. energy अच्छा यहाँ पे अच्छा मैग्नेटिक मोमेंट के साथ माइनस साइन एक मिनट इससे पहले नहीं it is from if you have seen this thing uh, magnetic field so it is just like you have जैसे electric field होता था ना so if you have electric field मैग्नेटिक मोमेंट यहाँ पे हम जो देख रहे हैं ना इलेक्ट्रिक फील्ड you see the magnetic moment here because if it is an electron here it is pointing in the opposite direction because it is a negative charge so जो here this direction of magnetic moment mu is always so if this is the direction of your angular momentum in case of electron this is going like if it is a no it is if it has been a positive charge because it is negatively charged it is like this and mu b is because okay so so this is coming from your the Biot-Savart law you have that magnetic field and magnetic moment that you can from there you can if you try to derive this we can arrive at this equation energy of interaction because okay so uh, we'll talk about it in case of this if you have a positive charge so if it is a negative charge which is moving then it is the magnetic field and you have this is the direction of magnetic field then the magnetic moment will be pointing in opposite direction if it is a positive charge which is moving and you have apply the magnetic field then the direction will be same of this magnetic moment okay so in this case yes what will happen is that it is the attractive interaction so it is north pole south pole. So yes the formulation is kind of like the electrons that anything that you may visualize the dipole moment points from one end to the other so dipole moment that we are talking about will so this if you have a magnet ये तो बहुत फंडामेंटल है एक मिनट नॉर्थ पोल साउथ पोल होता है ना so you start from this and connects like this so something like this happens and the direction the moment that we are talking about it is yeah within the system it will be so so magnetic field that this is a magnet and if you are putting it in the magnetic field so it is because of the directions that overall it results in attractive So if this is a magnet interacting with, so as I told you, this electron is also behaving as a tiny magnet. I have some pictures like this. एक मिनट में उसको दिखा रहा था. I think when I was discussing this last class, सेकेंड सेमेस्टर में एक दो मैंने आपको इमेज दिखाया था जब हम वो डिस्कस कर रहे थे. क्या कहते हैं, ओके. सो इलेक्ट्रॉन जो है मैग्नेटिक, so it is a dipole. Electron itself which is a, आपको मैंने ये बताया था कि इलेक्ट्रिक फील्ड के टर्म्स में it is a electric one monopole, but in a magnetic sense it is a dipole. It generates a dipole, so it is a dipole interacting with a field. Because of this you are getting that resulting in attractive interaction if it is there. So the tendency would be align with the field. Aligning with the field, if it is able to do it, then you have lower energy. If it is opposed to the, if the magnetic moment is opposed to the field, the energy will be high. So these are two things that we keep in mind, and it is the attractive interaction of this thing. अच्छा, ये मैं पिक्चर आपको इंक्लूड करके लास्ट टाइम एक बार बता दूंगा हाउ वी आर गेटिंग इट. सो जस्ट आई विल क्लैरिफाई दिस पॉइंट with more pictures. I had somewhere, I put it there. Okay, so the first thing is that it is proportional. Or in case of, if you have positive charge, because it is a negative charge, and that's why we are having the direction is opposite. अगर ये proton होता, if it would have been a proton, then the direction would have been same. If this is the applied direction of magnetic field, and this, the dipole moment that we are seeing is like this, and so the proportionality constant that we are seeing here is, this is the gyromagnetic ratio. This is, there is another proportionality constant for the spin. This is also gyromagnetic ratio. In addition to that, there is factor 2. This is the G factor. It is, and this comes from uh, G factor comes from this thing, क्या कहते हैं? It is a relativistic effect. So that is the theory of relativity that Einstein has given. I told you this with spin, there is an issue that if you visualize it as a spinning top, then it happens like you have, so because of, so there is another, spin has an additional factor which is G factor coming in proportionality, and you will find that in drawing also you see this arrow is bigger. You see this arrow is bigger, this magnitude is much higher because of this factor which comes coming in now. So ये जो factor 2 का आ गया, इस वजह से ये magnetic moment spin वाला, you see, for it is drawn with a bigger arrow. So you have a additional thing coming in for the spin, that is theory of relativity coming in over there. And so for an electron, the sources of magnetic moment are spin. So spin, we are accounting for orbital angular momentum. So both, so the mu is proportional to the angular momentum, and you are having a gyromagnetic ratio in both cases. In case of spin, you are, another thing is coming up, that is G factor, which is so the two magnetic fields. So an electron, if it is spinning in, if it is orbit in this direction, so see the direction of spin. So right hand thumb, you apply right hand thumb rule, it is giving you up, the both the vector spin vector pointing up, the angular momentum vector for this orbital motion, that is also pointing up. In such situation, if you apply a magnetic field like this in the upward direction, the magnetic moment will be pointing in the downward direction. Okay, if the angular momentum now, okay, so this is the case for negatively charged thing. In case you are having a positive charge, that is a proton spinning, imagine a proton is spinning. uh, if it would have been a proton, instead think of a proton, and it is having a spin. So give it a spin, then the direction of angular momentum will be this spin angular momentum. Direction of mu will also be same. It will be aligned to the field. It is only in case of because electron is having opposite charge that you are having this kind of thing. Okay, so we'll see this. So that is because of the minus sign of the charge that comes into picture, and we'll learn more about this. So there is factor of 2 coming in, which increases the magnetic moment to twice its expected value. जितना expected था, simple consideration of gyromagnetic ratio and this, उसके comparison में it increases by a factor of 2 because of this relativistic effect coming into picture. And कट जा रहा है. So this is the factor E by minus 2. This factor is mu E minus E by 2m. This is the mass of the electron. If we are talking about the electron, so this is the factor that is coming in both of them, gamma E, and additional factor of 2 in case of spin. So now there could be two cases when you have orbital motion is like this. It is pointing upward direction. The spin is, so you can have two situations. The first one, we have in the previous slide we have seen that yes, spin is also, so this is in this direction, I is pointing upwards, sorry, L is pointing upwards, that is the angular momentum due to orbital motion, and the spin is also pointing upward. Now this is the case, so both of these are pointing like this. Now suppose that spin is pointing, you change the spin, it is pointing down. In this case, the direction of the magnetic moment, this is the magnetic moment, which is so this magnetic moment is now pointing upward. So what happens in this case, you have, so in both cases we are assuming that the magnetic field is applied in this direction, this is the direction of applied magnetic field, and so the total summation, the total angular momentum will be a sum of both the things, the orbital plus the angular, and this is what we have been doing in second semester when we were talking about J. The J value was the summation representing the summation of the uh, two momenta and their relative, taking account into their relative orientation. So this one is the position thing that both the magnetic moment are aligned against the applied magnetic field. This is a high energy situation. So this will be so they are opposing the magnetic field, and so the energy would be high. Whereas in this case, at least one of the angular moment, magnetic moment, is now aligned with the field, and your energy will be lower. So general tendency will be that aligning with the field gives you lower energy, opposing the field will give you higher energy. So in this case, both the spin angular momenta, the magnetic moment due to the spin the magnetic moment due to orbital motion, both are pointing in the opposite direction to the B, the applied magnetic field. Whereas in this case, at least one of them is pointing downwards, pointing in the same direction as the magnetic field. So you have a lower energy is there. So when the magnetic dipole moments are anti-parallel, so anti-parallel magnetic dipole moments, the energy will be, so here the two, this is 1, this is 2, they are anti-parallel to each other. This is giving you lower energy, and spin angular, so when you have spin angular momentum, so lower, with a lower value of j, and with a high value of j, when both are pointing in the same direction, uh, you are having high energy. So this is the reason for splitting of the energy levels that you see in a typical thing. So ignited power